Now you recall that we had both a normal stress and we had a shear stress. In the case of the normal stress, remember there was some cut area and we had a component that came out of the area perpendicular to it or normal to it. The shear stress, on the other hand, we had the cut plane and it went parallel to that. Now what we've already seen then, that for strain we have epsilon, the normal strain, and that looks at the change in length of a line element. So it either gets smaller or it gets a little bit bigger. So we have the change in length over length of a line. It doesn't have to do with an area. So it is a line, not an area. So there's a difference, of course, in the meaning of stress versus strain. But there are some parallels. So we're now in a position then to define what is called shear strain. So I'll bullet this and we'll say the shear strain. And what we're going to do now is rather than one line element, we're going to identify two, like so. Now I'm going to put those line elements in a specific direction. So one's going to be in the X direction, one's going to be in the Y direction. And they're going to be small. So this would be a delta X. In fact, that could be the same line element that we used when we tried to quantify the normal strain in the X direction. Then this would be our delta Y. So we got two line elements that are originally perpendicular. That's crucial. So we have two line elements. And again, when we say line elements, it's kind of assumed that they're infinitesimal. So they are very, very small, that are originally perpendicular. And that's important. So they're originally at 90 degrees. Then, after they're deformed, after the deformation process, there's a change in those. So they were here and they were here. And now they're, let's say, here and here. So those are the new positions. Like so. They're originally at 90 degrees and now they're in this. Now, this one has changed a little bit. Let's call that, I'm going to put in just an ad hoc symbol for an angle. I'm going to call that beta 1. And I'm going to call this beta 2. So now there's been an angle change between both of those. So we're now going to define gamma, and that's lowercase gamma. Remember, uppercase, I'll draw that off to the side. Uppercase gamma looks like that. Kind of looks like a hangman if you guys still play that, like when I was a kid. So gamma, and that is lowercase, that is equal to the shear strain. Now, I will put here, sometimes it's called engineering, or some people call it physical shear strain. But we're just going to call it shear strain. It's going to be good enough for us. But again, some people would use the label engineering shear strain, or they would call it physical shear strain. And we would put two subscripts down here. So we're going to put X and Y, because those are the two directions that our original infinitesimal line elements have. So there are two small elements originally in the X and Y direction, and we are going to define this as the change in angle. Now this is important. This is in radians, not degrees. So radians are a dimensionless quantity, and that's the quantity that we're going to be using. So when you deal with shear strain, you're going to want to put on the radians button on your calculator. So it is the change in angle between, this is kind of wordy, but that's okay, between two lines that are originally perpendicular. So it is an angle change. So gamma xy. Let's go ahead and box that up. So just like we want to think about normal strain as being the change in length over the original length, we want to think about the shear strain as being the change in angle between two lines that are originally perpendicular. And there are ways to do that. We could physically measure it. We could use some sort of experimental determination. We have mathematical techniques that we're going to be able to develop at least at some level to find out what that's going to be. The nice thing about this is we can now introduce a sign convention for gamma. Now remember, just as an aside, epsilon, if it grows longer, it's positive. If it grows shorter, and again, that's the original line element. If it goes longer, it's positive. So if it's in being pulled, positive. It's being pushed, negative. And that's very, very intuitive. Shear strain is a little bit different. And I've actually got a method that I invented. So I'm going to write that. I invented this. What I want you to do is to take either hand, your non-writing hand, and you've got your thumb. So I'm going to stick my thumb in front of me. So there it is. And then my pointer finger. They look like this. And I'm drawing them. Wait, I guess I got to turn it around. But anyway, my thumbnail is there. There's my finger. So those are your two originally perpendicular line elements. That's your pointer finger, and then that is your thumb. Now what I want you to do is, what happens when you take those and you make them move like this, like we had in our little definition. They come closer together, and that is no problem. That's easy for you to do. That is positive. But now I want you to take your thumb and your forefinger and move them apart. You might need a friend or an enemy to help you with this, and open them up like this and like this. So as you spread it up, it's okay. Ow, you're starting to hurt me. Ow, bad, negative. So as it opens, ouch, bad, negative. I guess I said plus if, I could say negative right there. You will never, ever forget that little memory device. So, that is so sweet. I'm going to put a box around that. So the sign convention for shear stress is very easy to remember. All you need is your thumb and your finger, and that's it. And you can commit that to memory. Now, what about the dimensions of both of these parameters? So the dimensions. Epsilon, remember, is change in length over length. So that's going to be a length, change in length, divided by the initial length. So we would say that it is a dimensionless quantity. It is a dimensionless quantity. Or you could go ahead in the units. Some people would put meters per meter or inch per inch. All of those are okay. It actually doesn't matter. So it is going to have the exact same units because they're kind of artificial because they divide out. But most of the time we want to think about strain as being a dimensionless parameter. Gamma, on the other hand, is also dimensionless. Remember, it's an angle change, so officially it's in radians, which is also a dimensionless quantity. Like so. So they're both going to be dimensionless, but my recommendation to you is, when I ask you what are the dimensions of normal strain, you say dimensionless. When I say what are the dimensions of shear strain, I think it's a little bit better for you to say radians. Both of these are okay. So they are the same thing. But in my opinion, reminding yourself that it's in radians really helps you to remember what it's going to be used for. Now, the mathematical definition then is very similar. Remember how we did the partial u, partial x for the normal strain? The same thing happens with gamma. If I take two line elements and I move them like this and like this, and we're only going to show this very quickly. This is delta y, this is delta x. And we can basically say that that is going to be some change in the x displacement. So that would be a delta u. This would be a delta v, where v is the displacement in this direction. U would be the displacement in this direction. So U is the displacement in X, V is the displacement in Y. And now we can get that beta 1 that we had would be equal to the arctangent of delta U over delta Y. But for a small angle, the opposite over adjacent is the same thing as the, tangent of theta, or tangent of beta 1 is beta 1. So I would say that tangent of beta 1 is equal to the delta U divided by the delta X. And then the tangent of beta 2, I might have switched these around, I can't remember, is going to be the delta V divided by the delta X. I beg your pardon, this should be delta Y. And so in the limit, as both delta X and delta Y tend to 0, we find that gamma xy is equal to the partial of U with respect to Y plus the partial of V with respect to X. Now I'm going to put a dash box around that because I don't expect you to memorize that one. That's a little bit more complicated. We actually look at that in, again, Civ 560. That's really more of a graduate level topic. But I just wanted you to realize that there is a connection with partial derivatives, and so we've got the strains are related to the derivatives of the displacements, or we could sometimes say the gradients of the displacement. So strains we obtain by differentiating the displacement. I'm using a lot of abbreviations, but that's because we're approaching 12 minutes. And that means to get displacement, we integrate strain over length. So that to get the displacement, we integrate strain over the length. Remember, to get force, we integrated stress over area, so there's something very similar here. And the good news is we're only going to do this in really kind of simplified form for this class, but I want you to be aware of that. You get displacement by integrating the strain, and B is done.